Cycle 4, Lesson 3. In this lesson, we're going to look at applications using trig functions. And again, just like the last two lessons, we're going to be looking at some word problems and seeing how we can use algebra to help us solve these questions. The first one, the range of an arrow shot from a particular bow can be modeled by the equation r equals 100 sine 2 theta, where r is the range in meters and theta is the angle in radians above the horizontal that the arrow is released. The target is 80 meters away. Okay, so the target is placed 80 meters away. That's going to be important. What are the restrictions on the angle theta justify your answer? Well, if we imagine a sketch, and we have our archer at the origin, and the target somewhere in front of him. Let's say the target's over here somewhere. So archer, target. And then obviously the archer will need to aim maybe this way, or this way, or this way, something like this, so that allowing for gravity, if the archer aims this way, then gravity might allow it to come back down and hit the target, or this, something like that, right? But what can't happen is if the archer then leans so far back there, in fact pointing back over their head, then they're not going to hit the target. The arrow is going to go up and it's going to come back down over here, possibly injuring someone behind them. We don't want that to happen. So it has to be somewhere between the x-axis and the y-axis in quadrant 1. So that means it's got to be an angle between 0 and, in degrees, 90 degrees, but in radians between 0 and pi over 2, because pi over 2 is our equivalent, or our radian equivalent to 90 degrees. So theta must be greater than 0, but less than pi over 2. Being exactly 0 would be a problem because that would be straight along the ground. Pi over 2 also has its problems. That means that our archer is shooting it straight up in the air and is quite likely going to get hit by his or her own arrow when it comes back down. So we won't put the or equal to signs underneath. And by the way, pi over 2 is equivalent to 1.57. In other words, half of pi, half of 3.14 is 1.57. So that's the radian measure as a decimal. Now, part B, determine the angle or angles that the archer should use to hit the target to the nearest hundredth of a radian. All right, so we have the formula. R equals 100 sine 2 theta. But we also know that R is 100. R is the distance, the range. So I can put 100 in for R. And now we've got an equation, and just like any equation, our goal is to solve it now. So I'd begin by simplifying. I could divide each side by 100 for starters. And I get 0.8 equals sine 2 theta. And 2 theta, well, actually, let me back up for a second. To continue isolating things, I need to then get rid of the sign. So I can take the inverse sign of each side, and I'll get sine of inverse of 0.8 is equal to 2 theta. And calculator, set to radians, 0.8 inverse sine is 0.9273. So 2 theta equals 0.9273. And that means, so that's double what theta needs to be. So if I take half of that, then theta equals 0.46 if I go to the nearest hundredth. So that's one possible answer. But there is another answer. Again, let's think of this, and maybe I should have done this earlier. Instead of, we always like to think about the related acute angle. So if I go over here, and instead of talking about 2 theta, let's just say sine beta equals 0.8. Then, of course, that means that beta, when I do inverse sine of it, is going to be 0.93. Let's round it. And if we combine that with the cast rule, and the fact that this here is a positive ratio, right? Sine is positive here. So we're going to have our answers in quadrant 1 and 2. So we'll have an angle of 0.93 here. And another angle of 0.93, related acute angle that is, of 0.93 over here. Now, this is not, you may be thinking I just said that we can't do things in quadrant 2, but I can, because that's not theta, that's beta. Beta is, in this case, is 2 times theta. So I can, once I find out what that angle in quadrant 2 is, I still have to cut it in half. So we already found out that one of our thetas is half of 0.93. That's in quadrant 1. So I'll call that one theta 1 in quadrant 1. But theta 2 is going to be half of this angle here. So that will end up in quadrant 1. That will be a suitable answer. In other words, let's just do it. If I clearly pi, let's see, write it like this, 2, and let's put the 1 there, call this theta 2. So 2 theta 2 is going to be equal to pi minus 0.9273. In other words, again, on the sketch, pi would be a full, or a half rotation. We're doing a half rotation minus beta, so that's half rotation is pi, all right? So working that out, what we see is that we get 2 times theta 2 is equal to 2.2143. And then I can divide that in half. And theta 2 is equal to 1.11. And that would definitely be in quadrant 1, because remember, in quadrant 1 is anything between 0 and 1.57. 1.11 is between 0 and 1.57, so we've got this other angle. So the interpretation of it then would be, here's the ground, here's an archer with their bow and arrow, and they're going to shoot their arrow at a target over here somewhere. And so they do one angle. There's 2 shots they could make to hit this target. One shot goes at an angle of 0.46, which 0.46 is going to be about 30 degrees, a little bit less than 30 degrees, again, to put it in perspective for what you can picture. So maybe their initial angle is about that much, from horizontal, that's supposed to be. And if they do that, it's going to come and hit the target, and they're good. But they could also do 1.11, which is a much steeper angle. And so if they aim up more, that would also work, because what happens is it's going to come back down and still hit the target. And so there's two paths that lead to the target, and those are the angles that work in this case. Second example, a boat tied up at a dock bobs up and down with the passing waves. The vertical distance between the high point and the low point is 1.8 meters. And it repeats every 4 seconds. Determine a sinusoidal model equation to model the vertical position in meters of the boat versus the time in seconds. All right, so they don't tell us how to set up our sinusoidal model. So they don't tell us if we're starting at the top or the middle or the bottom of a wave. So that's going to be up to us. They also don't tell us. They just say the difference between the highest and the lowest is 1.8. So with that lack of direction, I will just make some assumptions. I'll assume that the low point is at 0 meters and the high point is at 1.8 meters. And if it's 4 seconds, that's 1 cycle, right? Let's put that here. That means half a cycle is 2 seconds, a quarter is 1 second, 3/4 is 3 seconds, of course. That's not even. That's a bit better. Anyway, so we know that the amplitude is half the distance between the max and the min. So max plus min divided by 2, that's going to be 0.9. The axis of the curve is going to be the max plus the min divided by 2, which is also 0.9. I can draw my axis of the curve on here. I always like to do that. So that's at 0.9. Let's just get a horizontal line to represent that. And now maybe I can draw my sketch. So they don't tell me where to start. I'm going to start where since I'm supposed to be doing a sine curve, I'll start right on the axis of the curve. So it's going to hit the max at 1 second, the min at 3 seconds. I still don't have that in a great spot, do I? I'm going to move it one more time. And that wasn't the min though, was it? Okay. Sorry, let me just adjust a little bit here. Okay, the minimum is there, and then we're back at the axis again at 4 seconds, ready to start over. Here is our graph. If I draw it like that, then that means that there's no horizontal shift, so I'll just say d equals 0, and my k value is 2 pi over the period, which is 4 seconds, so it's pi over 2. So my equation is y equals 0.9 sine 0.9 comes later, pi over 2 x plus 0.9. So A, K, D, C in that order. There's my equation. That's part A. Use your model to determine when, during each cycle, the boat is 0.5 meters above its mean position. Round your answers to the nearest hundredth of a second. So here's a picture of 4 seconds, 1 cycle. 0.5 meters above the mean. The mean is the axis, the horizontal axis, the C value. So we want to find it at 1.4 seconds, right? 0.9 plus 0.5 equals 1.4, not seconds, meters high. So we want to find it, if I had to estimate, somewhere around here. Here's 1.4. So for part B, we want to find the points of intersection between that dotted line I just drew in purple and the graph. I'm just doing that so you can see that you get a pretty good idea of when it's going to happen. Somewhere around 2/3 of a second and 1.5 seconds. Now that's a rough sketch, but somewhere around there. So somewhere in the first half of the cycle, the way I've drawn it anyway. But to be precise, we need to use the equation. So I'll take the 1.4 and put it into the equation that I just developed. So now I have 1.4 equals 0.9 sine pi over 2x plus 0.9. And like with any equation, I want to solve it. So I will subtract 0.9 from each side. I'll divide each side by 0.9, right? That's where these different 0.9s are coming from. And I'll have sine pi over 2x. And then I can take the inverse of each side. Let's find out what 0.5 divided by 0.9 is 0.5 repeating. So I just worked out what that fraction on the left was. 0.5 repeating, that's what the dot means. So I can take the inverse of each side now to get rid of that sign on the right. So I could do sine inverse 0.5 repeating equals pi over 2 times x. And so the inverse sine is 0.589. That picture disappeared for a second. There it is. 0.589 equals pi over 2x. And then I can divide both sides by pi over 2, which is the same as multiplying by 2 and dividing by pi. Again, where did that come from? The 2 came from here. I multiplied both sides by 2, divide both sides by pi, right? And then I have x by itself. Just shut down on me. Times 2 divided by pi, 0.3750, 0.375. Okay, that's what I got for x. However, once again, that is not the only solution. We already know that we're expecting 2 solutions, and I guess I shouldn't have used x. I'm going to fix that because, again, I can. I'm going to change those all to t. T? I guess I was thinking that t was part of this, the equation given, but no, I picked x. All right, I'll stick with x, but we'll know that x is the time. Anyway, we saw from the graph there's 2 different solutions. I got x equals 0.375. So maybe my sketch was off by a little bit. Maybe it should have been a bit farther over this way. Maybe I should have had a little bit lower down. I don't know. So it should have been a bit farther over here. So at about almost 0.4 of a second, a little bit less than half a second. Anyway, that's only my first solution. I still need to know what this second one's going to be. And again, we can do that by thinking about the terminal arms and the cast rule and so on. So draw a sketch, draw a Cartesian plane. We know that x equals 0.375, but that's basically our beta as well. So beta is going to be my goodness. Sorry. 0.375. Now this is not in radians. I'm picturing this as 1 full cycle takes 4 seconds, right? So I'm thinking of this in terms of the actual time now. 4 seconds is a cycle, which means that half a cycle is 2 seconds. There we go. Putting that together with the cast rule, obviously we need positive time, so my other terminal arm has to be in quadrant 2. So my related acute angle is 0.375. So my second time, x2 let's call it, has to be the 2 seconds for half of a cycle minus 0.375. So here's x1, one solution. And my second solution, x2, is going to equal the 2 seconds for half a cycle minus 0.375, which is 1.625, I guess. And that, again, that matches up pretty much with what I've drawn right here. So that's my second solution. So you can see in one cycle, this is the idea of a boat going up. So the way I've drawn it, the boat starts to rise. After about 0.375 seconds, it hits this height of 1.4 meters, keeps going till it gets to 1.8 meters, right? Let's draw it out. So rising, hits 1.4 meters, okay, at 0.375 seconds, keeps going to 1.8 meters, then it starts to come back down. Now it's 1.625 seconds on its way back down. Now it has to sink all the way to its minimum point and then rise again, and then it's going to start over. And in the next cycle, at 0.375 seconds into the next cycle, it'll hit 1.4 meters again, and so on ad infinitum. All right, and that is that.